Okay, so the exercise topic, system fundamentals, meaning how to find out if a system is linear, how to test linearity for any system. Okay, I have been kind to you. So basically only one. I used to actually have the linearity, causality, time shift invariance, and also the stability question there. But this year I have only the linearity, since that's actually the most important property in the sense that can you actually describe the system with a simple transfer function, just, which means that difference equation means that you can then make an implementation on the computer. Okay, but how to test system linearity? I will show you some tricks how to do it. Then, oh, maybe I should actually add an empty line here, there. Oh, great, this is so. No, well, that looks better. So, then the second question is actually paper and pen exercise. There's a flow diagram for a system, and the name of the game is follow the signal flow. And for any this kind of system, you just start following the signal flow and try to define what is the output for the given input, and then form it as a differential equation, meaning in this form. So if you get your equation like that, then you basically just, okay, then you have the system coefficients already. Okay, and then let's see, determine the difference equation for this system. Then the question is, what are the system parameters A and B? There you need to be careful. What are the A's and B's? Two simple mistakes you can make here. Swap the A and B, meaning you are swapping the zeros and poles, meaning your stable system is unstable. Most of the cases, or critically stable. So careful when you are basically defining the system coefficients A and B. Okay, and that actually another one is very simple mistake to do. When you first determine this difference equation in this form, so yn equals to something, okay. So let's think that you have the difference equation, meaning how to calculate the output for the input looks like this. Minus, okay, a k times y n minus k from 1 to n. So okay, so the second common mistake you can do here, so in addition to swapping that, is to have a sign error when you move these output terms in the left-hand side of the equation. Okay, now you have been warned, and some of you still will do that mistake. And this, almost everyone will do it once. Well, that will mess up the system. It's the kind of button to have a total malfunction of the system. Yeah, that actually, although this sign error can make the system unstable. Yeah, it can. Not always, but it can. Okay, so be careful when you are following these signals. What else? System coefficients. So system parameters, system coefficients, they are these values, the whole vectors. But we'll practice a little bit of that one. And then calculate zeros and poles and determine if the system is stable. Okay, hint here. System is stable if the poles are inside of the unit circle. All poles. Okay, then there's a difference equation given. So up to here, part 2, 3, and 4 are for the system which was defined by the flow diagram. Number 5, 6, and 7, and 8 actually are for this system. It's defined by a difference equation. Okay, so determine the parameters A and B for the following system. Nothing fancy. Check if the system is linear. Write your answer, justify why you think it's linear. Calculate the zeros and poles and determine if the system is stable. Okay, and then basically there's some graphing or drawing to do. Flow diagram for this system, meaning that nice box with only 3 kind of the blocks there. Add, scale, and the delay. Yeah, had to think while. Okay, what kind of drawing I want to see here? Well, any drawing that I can recognize, so you can actually draw it on pen and paper or paint or whatever is your favorite drawing tool. You can borrow a whiteboard too if you want to. All right, then we have a sound sample quite similar to the first exercise, except now, since you already know the this how to define the signal to noise ratio, actually the amplitude of that noise is should be given or marked as that one. Yeah, not the signal to noise ratio, but the amplitude of the noise, meaning the standard deviation of the noise. So this is directly the scaling factor. Okay, and then basically, wow, we have a system and we have signal. We can now run the signal through the system and listen what is the difference. Okay, a little bit of say practical stuff here. This is actually a let me see. 2.7. Actually, it's 2.5. Sorry about that. Question 2.5. There. Okay. Good. All right. And next, what does it look like when I take off? So first check was for the linearity. So back to the fact that, okay, test if a system is linear or not. And basically, what we can do is if a system is basically defined by, say, a function f, whatever that is. Whoops. So basically, linearity requires that if you have a sum of weighted inputs, and that is the question, is that the same as a, can you take that scaling factor out and also break the sum? So that's the linearity test right there by the definition. So what we need to do to test it, we calculate this one and then use the same input and scaling to calculate that one. That's as simple as it is. So that's the test. If they are equal, then basically the system is linear. And to basically prove it totally mathematically correct would require some heavy mathematics, but you will be engineers. We use brute force approach. Meeting random numbers. Ha! This should be actually valid for any value. We take any value we know. This must be vector. So that is random value or random vector. Same here. That's also random. This is random value. Singular value. Just a single value. Same here. We take two single values and two random vectors. Any. Well, let's see what Octave gives us and we use them. Okay. So let's think of a system. Since I have been telling that this kind of system is always linear time invariant, let's try it just for fun. So basically test if this sort of equation gives you the passes the linearity test, and we have had this 4-point running average, for example. That's this form. So 4-point running average filter. So y of n equals 1/4 of x of n plus x of n minus 1 plus x of n minus 2 plus x n minus 3. Okay, that's the difference equation. Wow, I broke it. Do I have to pay it? Wow. This is like IKEA furniture. Some assembly required. Okay, so basically the system coefficients for this system. Well, I don't need that one actually. So that actually describes my function. That's my function. So what I need to do, I will calculate first the output when the input is x1. Yeah, I can do that. I just need to give you a couple of hints how to do that. So how to make a delay. We need 1-step delay, 2-step delay, and 3-step delay. Maybe I will see if there the help first. But anyways, let's test for linearity. And my system is output equals quarter times x of n plus x n minus 1 plus x n minus 2 plus x n minus 3. I hope that one went somewhat correct. Oops, n minus 19. Yeah, sure. So this is just a comment line. So that's my system. And what I would need to generate these for calculations. I need to generate those. Let me check if there is the delay operation in Octave. Delay. I have no idea. Does it have? Oh no. This gives some. No. Function reference. Is this the delay I'm looking for, or delay vectors? Time series delay. Produce delay vectors. Function of assumes that each time series is a long number. I don't think so. I have no idea what the person has been writing here. So what I can actually do, we can also use the delay so that we will just shift the data. There is actually a implementation of the system, but you don't know that yet. Let's do it as the mathematics say, just for the fun for it. So how to produce that delay? Well, we move the data right by shifting it. So we add one extra element on the front of it and take one off. Okay, let's do it. However, that actually messes up the test a little bit, because now we are introducing something to the data that does not exist there. But we can take care of that. Okay, so anyways, let's now find out these random numbers A and B. So any numbers for the test. I have A equal to rand n 1 1, meaning one random number. Yeah, that's a random number. Try that one. You probably get the same value. So what is the random number if it gives that same number all over the way? Does it say same? No, it's not the same. Excellent. So basically, if you get the same numbers I do, it means that you haven't used a random number generator yet. If you have, then it's already randomized. These are semi-random numbers, meaning it always starts with the same seed number. Okay. But anyways, that's one random number. Then I need another one. So random 1 1. Okay, that's my B for that one. And then I need two random vectors. And I will take, actually, let's take 1000 by 1, meaning, okay, let's see, is it 1 by 1000? Well, that doesn't actually make any difference here, does it? So, okay, rows and columns. One column, 1000 values. Maybe we'll do it that way. So one row, 1000 columns, 1000 values 1,000 random values. And then we take another one, which is also the same thing. But of course, these are not the same because every time I call it, it gives me different numbers. So those are different. Yeah, that's good. So those are totally independent of each other's random values. And now we can start calculating that part, left-hand side part. Okay, so we basically combine these to x3. So weighted input x3 equals a times x1 plus b times x2. Right, was it? Sorry, I forgot my rule of thumb, never use single letter. The variable names. Okay, so a times x1 plus b times x2. So we now just need to put this signal into my system on the point of that one. It might be actually a good idea to write this as a function. Should we try that one? Maybe we should actually try that one. So how to make functions in Matlab? That's pretty easy. Let's start a my function, for example, my func. That's a good name, func. If you edit a file which has the M at the end, it's basically automatically a M file. It's a text file. You can edit with any text editor. It's readable, human readable form, and you can call these from Octave. So basically, just figure out a reasonable name for the function and then just press enter. File does not exist. Do you want to create it? Yes, create. And it opens, well, here. Wow. Lots of text already there. That's nice. That's nice. I will get rid of most of it. So basically, but anyways, it also shows you. Well, you might actually just leave this one here. So basically, you can then add some parts here. So this will be also the help file. Whatever is on the beginning up here, when you type help, oh, actually it's here. When you type help, it appears on your screen. So if you go on the command window and say help my func, oops, it's not there yet. Sorry, I didn't save it. When you save this one, then you can actually start using it. My func does not. Strange. What? Func. Oh, that's why. Func. Where the heck did it get the func? Didn't I start the edit? Oh, yeah, okay. That's my func. Okay. My func. Good. Help. Yep. That's basically same text as in here on the beginning. All right, but anyways, that's the function prototype. Return values, and then input values. In our case, we have just one input. Right. Our input is X. Our output will be Y. And inside of this one, we'll write whatever this function does. So output equals 1/4 of that. Which means that we now need to do the delayed X, XX1 equals, we take 0 at the beginning, and then XX from first to almost last value, length of XX minus 1. Okay. Sorry about those colors not showing up. So for some reason that yellow does not show up. So there's 0 basically added to the beginning of the data. So that's shifted. Oh wow, maybe there's a shift operation actually on Octave. Let's see if there is shift, since that will be so much more elegant way of doing it, although it does exactly the same thing. I don't have internet now. Oh, great. Oh, shift here. Help. Shift. That takes for a while. Anyone has an internet? Okay, Shift X. Okay, Shift X and how many bits? Okay, that'll do actually. We can use this shift. Okei, mulla on kato samanlainen mokkula, mutta tämä ei. Se ei ole vaan netissä. Oi, sushi wifi. Tää tulee semmoiset hampaanjäljet. All right, but anyways, it looks like we have a shift operation. So shift of our data vector, how many data points? So basically 1, 2, or 3. So that's actually shift X1, shift X2, shift XX3. Good. Back to the editor. So basically I can do it like this. Shift XX and 1. Okay. And basically then XX2 would be shift XX2 and where did my and still those values don't show up, not even there. I should actually change the colors. Okay, those are now the shifted data. You can actually just write one line and do the thing, but I usually like to do the this mid results just because computer does it in anyways. Even if you write one long line. A nice thing about C programming language, you can write any program just as a single line of code. Okay, so now I can make the output YY, which is YY equals 1 divided by 4 times XX plus XX1 plus XX2 plus XX3. Right. Okay, that's my function. And now I can call it. Save it, and calling my func would return this value. That's how easy it is to make functions. Some of those functions on exercise are actually a little bit awkward doing this way, but yes, they can be done. And it also teaches you about which is system property and what is single property. Since whatever you do for this linearity check, there can be only one input which produces one output. No other parameters allowed here. No global variables either. All right, save that one. That's save, right? Save, and now we can test if this system is linear or not. So yeah, that was the x3 we had somewhere. Yes, x3. Calculate f of summed input. Summed input. Yeah. What? What is that? Where did this one come from? Dimension. It just appeared there. Well, whatever comes for free. All right. So, not the perfect system. So we have this fx3 equals, meaning that system output for my summed input, not think. X, was it x3 or x3? X3, yes, x3, there. Oh, I see. Mm-hmm. Okay, now it works. So basically, it was still on the some other mode. Okay, now I calculated fx3, which is the system output for the summed input. That one, done. Now I need to sum the system outputs for those inputs. Okay. And sum them. Okay. So I call it fx4. A times my think as when the input is x1 plus b times my think when the input is x2. Okay. I'm calculating this one, fx4. The question is, now, is the fx3 same as fx4? If they are the same, then basically the system is linear. If not, then it's not linear. I will get not linear because actually the shift inside of that function adds some extra information which is not there in reality. So we actually can compare only the part we know that we did not put any artificial data in it. So we added that shift function adds extra zeros on the beginning. So we need to get rid of those. Otherwise, we cannot rely what is coming up. But I'll show you now basically the results of that one. So how to test if these two signals are the same, we can actually, I will just plot the difference just to make a point. So I will plot fx3 minus fx4. Wow, this came out actually pretty nice. Wow. So the zeros did not make much difference here, although they are still affecting on the beginning. What you would say, does this one mean that the system is linear or not? Look at the numbers here. E to minus 16. What is the machine epsilon here, which is the smallest number? Dual precision floating point. Eps. That's the machine epsilon. So this is roughly the computing accuracy for any computation. 2.2 e to minus 16. So basically, looking at the figure, they are all within the error margin. So this quickly, I would say this is linear system. But well, let's do some real testing, since these are considered as vectors with 1,000 dimensions. Okay, how to test if two vectors are the same? You calculate the distance. It doesn't matter how many dimensions it has. We have 1,000 dimensional system now, you know. But you can still calculate the norm of the difference. All right, so calculate the norm of fx3 minus fx4, but actually for this one I would take out some of these variables I know which are not correct. So let's take the artificial part out. Where's my so I will do it so that I will calculate the indexes. What I'm interested in actually is the 4 to length of fx3. All right. And then calculate the norm of fx3 of ins minus fx4 of ins. So now we know for sure that this does not have any artifacts on the data. And this is case by case. If you shift data, you always have to take care of that part. Okay, and we still have quite reasonably close to this the machine epsilon. So basically, machine epsilon multiplied by the square root of the number of points you had there. If this is less than that, then this is practically 0. This is 0. I call it 0. Zero. So machine epsilon times where the square root of number of n comes from. Well, this is tough statistics. How many, you know, what is the, oops, eps. Why didn't it give me eps? Ans times square root of 1,000. Yep. So yes, that is less than the statistical error made by those 1,000 numbers. Okay, that's less. 0. Okay, it takes a long time to prove that the system is linear. Yeah, well, but that's life. It's called engineering, but anyways, now you learned also how to make these functions on Matlab. So if you use function on the exercise, please put links to the functions also, or copy paste the text. Good. The next part. Wait a minute. Where do I have it? Oh, no, there, not there. Exercise 2. There we go. And next, all right, how to determine the system coefficients from flow diagram. There's absolutely no magic on it. You can figure it out by yourself. I'll just give you a couple of points there. Just a couple of pointers. So basically, if you have a symbol like that with any number inside of it, I just mark it A, then the output would be x n, A times x n. That's simple. After that, basically, if you have a delay, this is an example. If you have a delay here, whatever is inside here will be delayed. So you have A times x n minus 1 as an output. And then on the sum, whatever you have as another input. Okay, let's make it simple. If I add that one as the input here, this is A, x n minus 1, and here we have A times x as our inputs. So the output here, yn, would be simply A times x n plus B times x n minus 1. So you just follow this diagram. Actually, if you double click the diagram, you can get it bigger. You can see it bigger. Okay, so basically just follow the signal flow. That's simple on the second part. Second part, third part, system parameters. Okay, now you just need to be careful. Remember what I have said about the... So you calculate the output following the signal. That's something. In form of that, you have basically sum of the, for example, like this, B1, x n minus 1, and so on, and then you have minus A1, y n minus 1, and so on. That's the difference equation. System parameters you get when you move all the parameters of y on the left-hand side and leave all the parts that have x on it on the right-hand side. And then you have a corresponding parameter, AK, correspond to delay k, same for that one. And the parameters are basically vectors B for x and A for y. So that 4-point running average what we had. The 4-point running average. Where's the cursor? I lost my mouse there. Okay. System coefficients or parameters. They are basically the B in our 4-point running average would be 1 quarter, 1 quarter, 1 quarter, 1 quarter. Simple as that. So that's the B0, B1, B2, B3. Similarly, with if we have some of these delay terms are missing, that will be 0 in here. Okay. To be on the safe side for the parameters A0 is always 1. That's the multiplier factor for output. 1 times yn. Then basically we didn't have anything else. So it's 0, 0, 0. That's the safe side. On the other hand, for the calculation point of view, you always have the intermediate of or leading zeros on the system, but if you have these tailing zeros, you can leave those out. But be on the safe side, we have BNA. Like that. Yeah, those are the system coefficients. I expect similar answers from you, although the system is totally different. Key. What next? Zeros and poles. Oh, this is so difficult. Draw zeros and poles on Argand's diagram. I didn't say anything about Argand's diagram, but let's see. It might be easier than you think of. So basically, I hope I have this package here. Maybe Z-plane. If it gives you error message, it means that you need to download and install the. Oh yeah, function belongs to signal packets. To load the packets, run packets load signal. Okay, and then yeah. Let me try. Yes, I have internet. So packets load signal. Okay. Okay, those are the zeros and poles on Argand diagram. 0 pole plane. Poles are on the origin. Actually, that's a triple pole. And then we have 3 zeros on the unit circle. No magic, it's just Z-plane. So this morning lectures, I've spent a lot of time to explain the zeros and poles. I could have just run this. And what I needed is just the system coefficients to get these. So that's what you need to do for the system when you have the system coefficients. Next thing was, wait a minute. And there we have K, and then basically determine the A and B for the following system. Okay, there we have another system which only has the zero, no feedback. So this is similar to my example here. I don't say more. Check if the system is linear. You know that, how to do it. Calculate zeros and poles, and determine if the system is stable, and draw flow diagram. Okay, you should be able to do it by now. Okay, next is actually quite interesting. When you have this some sound sample, for example, that kind of sound sample, then you can actually use the system coefficients and try to filter the system with that, filter the signal with that system. Okay, I'll show you how. First, I would like to see, let's see, I will open that one and find my last time. All right, what did I do? Okay, basic note. 440 hertz sound. Why I have done that more than one time? Well, maybe. Okay, run selection. Yeah, that's my signal. Hey, I have that SS2 here. Great. Run that one. And then even, okay, that's SX. And now I put some, okay, some noise calculations. And then I will go back to the command editor. Yeah, there. So my signal, my signal, my func and my signal. Okay, would be S. What is S? S plus SS. Oh, SX actually, yeah. SX plus plus NO. Yeah. And then what does it sound like? Sound, my, sig, and FS. Okay, so these are that. Pipe organ plus some noise. The question is how the running average filter affects on that sound. What do you expect? Running average actually reduces the high spectral noise. So it reduces the variation by the square root of the number of points there. That's basically statistics. The system linear time invariant system implementation in Octave is called filter. Okay. Filter equals LTI system implementation. And how to use the filter? Well, take a look at the documentation. I will just use it. So filtered my signal is filter. Then we have the system coefficients. Did I save those filter coefficients somewhere? Okay, B, B, and A. Yes, I did. Good. System coefficients in this order: B, B, A. By the way, when I called the this function to calculate the zeros and poles, it's always the BB coefficients first and then AA coefficients. So input coefficients are called BB, output coefficients AA. Okay. So then my sig. There. So this is the signal after my filter. There. And now I can compare the sounds. Sound. What? Sound. Okay. My signal FS sounds like that. F my signal FS. Any difference? Yes, there is a difference. So they basically it's subtle difference since this running average filter is not too effective to reduce the noise. Yeah. More bass. Yes, later on Thursday. Well, actually, Yeah, tomorrow maybe tomorrow. Yeah, to boost. Yeah. So basically, that was quite settled change in the signal. But anyways, we have a running average system. It's not a great filter as you heard it. So basically, tomorrow and on Thursday, we will learn a little bit more effective ways of filtering data. But this far now, you know how to handle the systems. Everything comes from the fact that, okay, hopefully we have a linear time invariant system. You can define the parameters. First, you can actually check if a system is linear. Excellent. Then you basically can, from the this flow diagram, you can define the what is the system difference equation, which gives the system coefficients, which are the same coefficients as in transfer function. Although the transfer function calculates everything on the frequency space, different equation in the this time space, but anyways, for Matlab or Octave, basically you can use the same coefficients both on time and frequency space. Good, that's my part for today. Start doing the laboratories, and yeah, at some point we will go home. Good, thank you.